student, myself Pratisha Bhatt from Bombay Baba University at CSE branch K2 section. So, my today's topic for period 2 of quantum is quantum gates, the CNOT gate, the token, the Friedkin gate, and everything. So now I am going to explain all these gates. So my first gate is the CNOT gate. What is the CNOT gate? CNOT gate is a controlled NOT gate and it is one of the most important 2 qubits gate used in a quantum computer. It operates on control qubit and a target qubit. The main rule is simple. The target qubit flips only when the control qubit is in the state of 1. If the control qubit is 0, then nothing happens to the target bit. It just copies the target bit's input in the target bit's output. So, if we need to know more, so let's dive into the deeper section and let's get started with learning how we can describe the logic of our CMOS gate. So let's see the truth table of our CMOS gate. So now let us dive more into how the CNOT gate actually works. So as we already know that the CNOT, it is a 2 input and 2 output gate and it is analogous to classical XOR. The symbol for making the CNOT gate is like this. It is the symbol where X represents the control bit and this represents the target bit. So we needed the logic of how the CNOT gate works. So the logic behind how the CNOT gate works is if control bit is 0, then copy the input of target bit in the output. And if control bit is 1, then flip the input of target bit in output. So what does this mean? Let us understand this nicely here. When control bit is 0, then copy the input of target bit in output. This is our target bit and we need to copy this in here as our control bit is 0. So here we just copy it in here. Similarly, in this case, our control bit is 0, so that means we just need to copy the input of target bit in output like this. But what happens when the control bit becomes 1? So here is the twist. When control bit is 1, then flip input of target bit in the output. So as here it is 1, we are flipping the target bit's input which is 0 at in the target bit output and it becomes 1. Similarly here when control bit is again 1 and our target bit is also 1, so we are flipping it and it becomes 0. So here in this way we then write the matrix of CNOT gate. So now further we can understand more about the CNOT gate. Exactly, our truth table for CNOT gate is like this, which is control, target, and then output. And then the next thing we can understand is like how NOT gate is made using CNOT gate. To make a NOT gate through CNOT gate, we just implement the X gate as 1, which is input. Because what is a NOT gate? A NOT gate is simple that if we input 1, so then we should get as an output 0, and if we input 0 we should get 1 in output. This is what a NOT gate means. So for that, if we take x is equals to 1 gate, so then our answer would be obviously 0. So in this way we could make a NOT gate using CNOT gate. And then how can we operate CNOT on gates? So here are the various types of the questions that we could practice easily. So now let us move on to the next gate, which is the Toffoli gate. So the next gate is the Toffoli gate. So what is the Toffoli gate? The Toffoli gate is also called as CC NOT gate, which is the control NOT gate. It is a 3 qubit that has 2 control qubits and 1 target qubit. If it flips only when both the qubits are in the state of 1. If either of the control bit is 0, then the target bit remains unchanged. This gate is extremely important because it is both reversible and universal for classical computing. That meaning any classical logic circuit can be built using Toffoli gates. In quantum computing, The Toffoli gate helps us build more complex quantum circuits and is used in quantum error calculation, arithmetic operation, and building controlled versions of other gates. So, let us now try to understand the Toffoli gate more easily by seeing its truth table and the logic of that how the bit flipping happens in our Toffoli gate. So now let us see it nicely. So, as we already know that the Toffoli gate is also called as CC NOT gate, which is called as control NOT gate because it is having two control bits and one target bit. So now we could see that how the Toffoli gate is represented. So the representation is given like this way, and it is universal and reversible gate. What is the logic behind the Toffoli gate? The logic behind the Toffoli gate is that if both control bits are 1, then flip the input of target bit. It is very simple. Let us understand it by seeing the truth table. What does it means in here? If both control bits, like here the control bits are x and y, and then the z is the target bit. In the output also we have x and y, and then this is the z, which is the target bits output. So now the first condition is 0 0, but what we need, if both control bits are 1, then flip, or else just copy the target bits input in the target bits output as we were doing in the C0 gate. So this becomes 0. Similarly, in the next case, when both the qubits are 0 and here it is 1, so we just copy it in the output. Similarly, even if there is 1 1, like if one of the control bits is 1, then also we just copy the target bits input into target bits output. We need that both the control bits should be 1. Like in the last second condition, both the control bits become 1. So therefore we flip the target bits input, which is 0, into target bits output, and then it becomes 1. Similarly, in the last case, when the both control bits are 1, so we understand that we need to flip the target bits input as in the output. So here it is 1, and then in the output it becomes 0. So in this way we represent the truth table of a Toffoli gate. So then if we want to solve that how should we make a NOT gate using Toffoli, it is very easy. Like we just need to set x d, which is our control bit, is equals to 1, and similarly y, which is another control bit, as 1. So then when it is 1 1, we just need to flip the output of input of target bits in the output, 0 1 1 0. As we have understood previously that what is a NOT gate? A NOT gate is simply that gate that flips the inputs into output. Like if we give input as 1, so then we get in the output 0. So it is very easy to make a NOT gate using Toffoli and C0. So like this way the topic of Toffoli gate comes to an end. Now let us move on to our next topic, which is Fredkin gate. So now the next gate that comes, that is Fredkin gate. The Fredkin gate is also called as controlled swap gate, and it is the 3 qubit gate consisting of one control bit and two target bits. The unique property of Fredkin gate is that it swaps the states of two target bits only when the control bit is in the state of 1. If the control bit is 0, then the target bit stay the same without any swapping. The Fredkin gate is important because it is a reversible gate, meaning that the original input can always be recovered from the output. So now let us try to understand more about the Fredkin gate by constructing its truth table and understand its logic more nicely. So now let us see its truth table. So, as we know that our next gate is the Fredkin gate. So, the Fredkin gate is also called as controlled swap gate. It is the 3 input and output gates. It is universal and reversible gate. The symbol of Fredkin gate is as this. What is the logic behind the Fredkin gate? The logic behind the Fredkin gate is if input x is equals to 0, so then we just need to copy like the y dash is equals to y and z dash is equals to z. One thing we should make clear here, it is like there is only one control bit and two target bit in our Fredkin gate, so it makes it different from the any other gates as we have seen before. And the second logic is if input x is equals to 1, then we need to swap the target bits. So let us understand this more easily through the truth table. Like when the control bit is 0, we just need to copy like y is equals to y dash, z equals to z dash. Again, it is 0, so just copy it. Y equals to y dash, z equals to z dash. Similarly, we would do this till this step, and then when the control bit, that is x becomes 1, so then we need to swap. And how does this swapping happens? This swapping happens like here the y's value becomes equal to our z dash value, and then the value of z becomes equal to the value of y dash. So here both the qubits were 0 0, so it is not that much visible. But if we go to the next step and see when the control bit is 1 and here y equals to 0 and z equals to 1, here the swapping had happened. Y equals to 0 and then its value has gone to z dash value, and then z equals to 1, its value has came to the y dash 1. And then another example, here when it is 1 we need to swap, and here the value of y goes to z dash, and then the value of z goes to y dash. In this way the swapping happens in our Fredkin gate. So this was all about the Fredkin. So now the next gate is that the Hadamard gate. What is a Hadamard gate? The Hadamard gate is one of the most important single qubit gates in quantum computing because it creates a superposition. When a Hadamard gate acts on a zero gate state, it produces an equal combination of 0 and 1. When it acts in one state, it also creates a superposition, but with a relative negative place. So the Hadamard gate is represented by a single matrix and by the letter H in circuit diagrams. It is commonly used in the beginning of quantum algorithms to prepare qubits for parallel processing. So in this way, the Hadamard gate also plays a crucial role in quantum entanglement. So now let us see the next topic, which is the polygates. What are the polygates? There are three types of polygates: poly X, poly Y and poly Z. The poly X gate acts like a classical NOT gate. It flips the qubit when it is 0, so it becomes 1, and when the input is 1, the target bit, the output becomes 0. The poly Y gate. What is the poly Y gate? It performs bit flip and phase flip, and it corresponds to rotation of pi radians around the y axis. Poly Z gate. What is poly Z gate? It is also called as phase flip gate. It keeps the zero gate. It keeps the zero the same, but it flips the one state. This makes it useful for controlling phases, which is extremely important in quantum inference. Together, these all poly gates are used to build more complex quantum operations. So now let us understand more about what are the De Morgan's law. What is De Morgan's law? De Morgan's law are two very important logical rules used in mathematics, classical computing, and quantum logic. These laws explain how NOT operations interact with and OR. They allow logical expressions to be simplified and rewritten in an equivalent form. So, as we have practiced all these questions, so here, like this way, I want to conclude my today's explanation. So, I hope you all must have understood all the topics. So, in this way, I am concluding my topic of quantum gates here. Thank you everyone.